They're just delicious though. Anyway, so for number 2, it says we're finding the derivative of x squared plus the natural log of x. All right, so this is rule based. The first part is power rule. So x squared just becomes a 2x. Multiply power by coefficient, reduce the power by 1. The natural log, if I take the derivative of the natural log of x, by rule, I'm going to take 1 over whatever the argument is of the natural log function. All right. So in this case, we would be assigning the value of u to be equal to x. Du dx would be equal to 1. That's assuming we want to follow the rule. But there's also the part where you just memorize it. The natural log of x has a derivative of 1. But if we're following the rule, I would say 1 over the u, which is x, multiplied by du dx, which is a 1. And so we'd get 2x plus 1 over x. All right, and then simplify as needed. In this case, it's not needed. All right, but we take certain things for granted, like the natural log of x has a derivative of 1 over x. We just kind of rely on that information. But we also want to be mindful of the domain, right? So this is the instance where x has to be greater than 0. And if you're ever unsure, pop it into Desmos, put in the original function. All right, so that's my original function. And then just type in f prime of x. And just observe where this function exists. All right, whether it's the original or the extra crispy, you look at it and say, well, it never appears to be to the left of the y-axis. In either case, it appears to be asymptotic with the y-axis. Right? So it's actually never going to touch the y-axis either. All right. So that gives us a sense that the domain is restricted, and therefore we would conclude that it has to be the case where x is greater than 0. All right. So for number 3, we have a linear function. Then we have the natural log function. The whole thing is cubed. So we would want to use the chain rule here. Now, whether you're using the long approach, the longer format, or the shortcut, you should end up with the same result. All right. But we also, again, want to be mindful of the fact that it's a restricted domain. All right. So if you're not sure, again, you just type it in. So that's what my original function would look like. Oh, actually, sorry, that's what my derivative would look like. The original function is nowhere to be found, probably because we need to zoom out somewhat to get it. Or maybe zoom in. Maybe it's so tiny that we can't really tell. Now, I tried zooming out and zooming in, and I can't seem to find it. So one thing I could do is make a table out of this first graph and just see where the points are. All right. So if I hit that little gear icon, it'll allow me to duplicate the function or make a table out of it. It says undefined, undefined. But then after that, once we hit 1, it gets really huge, really fast. Right. So this is telling me that I want to be kind of living up in the large number territory. Right. So I'll undo that so I see the function, but it's telling me I got to zoom out a lot. But what I can do instead of zooming out is just make my maximum y value something really large, like 5,000. And then now I can see the graph. And then I can also look at the derivative graph. All right. So looking at the points will give you a sense of what's going on. And then from there, we can kind of go the distance. The benefit of the TI when it comes to stuff like this is that there's that ready-made table. All right. So if you're a TI calculator user, then all you do is hit second graph. You'll see the table of values, and you'll see immediately that you're looking at really large values that you can adjust from there. All right. But anyway, now we know what we're up against. We know we have that domain restriction. So I'm going to let u be equal to 8x minus 3 ln x. All right. So that'll be this part of it. So I would say y is equal to u cubed. And so u is equal to this. So applying the chain rule, I'd say dy du is equal to 3u squared. Du dx would be equal to, well, 8x goes to 8. Then this piece, we just kind of rely on prior knowledge. Natural log of x has a derivative of 1 over x. Hang on to your constant multiple and take the derivative of the parent function separately, and then just piece it all back together. All right. So dy dx, which would be the product of these two things, would also be thought of as f prime of x, 3u squared, all right, with the u really being the 8x minus 3 ln x, and then multiplied by du dx, which would be 8 minus, I'll write it as 3 over x. And we would say, I'm out of space there, so I'll write it below, where, or with, semicolon if you want, where x has to be greater than 0. What do you use u again? Well, we're using the u for the chain rule because we're looking at a function that's contained within another function. So under ideal circumstances, we would say, all right, I wouldn't want this here. I really don't want this. I would rather just be x cubed. If I have a choice in the matter, I'd say, okay, it's x cubed. But I really don't have a choice. Right? But what I can do is I can modify it. And instead of saying that big nasty expression cube, I can just say, okay, well, let's replace that big nasty expression with a u. And then look at them separately. So we would say, all right, if I'm going to let that big nasty expression be equal to u, then I can think of f of x as being equal to u cubed. All right. So that's where this comes from. But then separately, I'd have to say, well, u really is 8x minus 3 ln x. Piecing it all together down the line is what gives us our derivative, and it has everything to do with the fact that dy divided by du multiplied by du divided by dx, right? So dy divided by du multiplied by du divided by dx simplifies down to equal dy over dx. So by figuring out this derivative and then multiplying them later on, we're able to get the expression that we're looking for, which is dy dx, which in turn is f prime of x, which is what they're asking us for. All right. All by redefining this expression here by saying, all right, instead of this big nasty expression cubed, how about just u cubed? Right. So no matter how elaborate the expression is, we want to be thinking about it that way. So for example, I'll just jump down to number 6 because it's a similar structure. I'd look at this and I'd say, okay, well, I don't want ln to the 4th. I'd rather have something simple like u to the 4th. So I would say, let's let y equal u to the 4th. All right, so this would be really a u. All right, u to the 4th. But u really is ln of x. So I'd make a little note of that. U is equal to ln of x. Then I'd compute dy du and du dx. U to the 4th has a derivative of 4u cubed. ln of x has a derivative of 1 over x dy du multiplied by du dx simplifies down to dy dx, which in this context is f prime of x, which would be this expression multiplied by this one. For instead of the u, well, we know what u really is. U is really ln of x. So 4u cubed becomes 4 ln of x cubed multiplied by 1 over x. And that would be our derivative. I mean, you can clean it up further if you want. Not much to clean up. It would be, if you want, you'd write 4 ln x cubed over x. You write it like that if you want. But you do have to stipulate where x is greater than 0. Okay. But that's a case where we're applying the chain rule and also log rules. So it gets a little dicey that way. Right. But numbers 4 and 5, well, 4 is definitely easier than 5. I mean, you just look at them. But it's actually even easier than it appears. Right? Sometimes applying a rule that you might remember for logarithms will actually kind of help you. All right. So you might remember the product rule for logs. All right. The product rule for logs tells us that if we're taking the log of two terms that or two factors that are being multiplied, then you can split it up and write it as an addition. So this would be the same as saying the natural log of 5 plus the natural log of x. All right. You can also apply the rule above, the ln of u rule, but this is actually a little bit easier because this piece here is constant. So when I go to find my derivative f prime of x, the constant part, well, anything that's constant is not changing. Since the derivative represents a rate of change, the rate of change of something that of something that is not changing would be 0. The other piece would just be 1 over x. And so our derivative is just 1 over x, again, where x has to be greater than 0. All right. That's the kind of interesting one because you look at it and ln5 doesn't always present itself as something that would be constant because you see ln, you think ln, letters, variables, so it must be a variable of some kind, but it doesn't have an x in it, so that makes it constant. If you're ever unsure, Desmos will tell you. So type in ln of 5, and the TI will tell you this too. ln of 5. Desmos is saying the derivative f prime of x is 0. It's not saying 0 sometimes, sorry, sometimes, it's saying 0 all the time. It's telling us that the derivative is 0 for ln of x. That's pretty nice. All right. But if you want to go back to the original function, we had ln of 5x. So looking at that original function, I'll bring the zoom back to something a little bit more ordinary. Turn it off the second graph. If you're ever unsure that you're simplifying is, like you might think, okay, I'm pretty sure this is right, but I'm not 100% sure. Type it in as a separate equation, y equals ln of 5 plus ln of x. And just make sure that your two graphs, the f of x and the y, map to the same location. All right. And sometimes you get worried that your mind is playing tricks on you. So what I do, I've done this a bunch of times already, is I long press on the icon on the left-hand side, make one of them dashed, maybe a little thicker instead of 2.5 as a thickness, make it like 5, make it stand out a little bit more, just something to make it a little bit more obvious. And then when you really take a close look, you can see that they're mapping to the same location. All right. And then I would turn my derivative on, because now that derivative is relevant, because I know regardless of whether I'm dealing with the f of x or the y, I'm dealing with the same original function, both of which would have the same derivative of 1 over x, but only where x is greater than 0. All right. So looking at number 5, a little juicier looking than some of the other ones, but definitely very manageable. All right, I'm just going to reduce this a little bit. So we have 2 functions that are being multiplied. All right, so 2 factors multiplied. When you're looking for a derivative, that implies the product rule, but not the product rule for logs, the product rule for derivatives. All right, so I have my 2 components here. F prime of x would be my first function as is, multiplied by the derivative of the second one. But what I'm going to do is I'm just going to write it in notation form. I'm going to write it as d dx of ln of 4x. The reason I'm doing it this way is so I can kind of keep it straight, because I got to find derivatives within derivatives. So I don't want to confuse myself. So I just write it out in notation form first and then simplify from there. So that's first times the derivative of the second plus the second ln of 4x times the derivative of the first. Now that you can do in your head. So there's no need to use the notation form if you don't want to, but I already did it for the first part, so I'll do it for the second part also. So times the derivative d dx of 3x squared all right. So this is telling me, it's a little recipe. It's telling me, all right, the only 2 things I got to worry about finding the derivative of would be this piece and this piece. All right. Now, if you compare this, what we just did, or when we compare this with what we just did, we just figured out the natural log of 5x, the derivative of that, and that was 1 over x. And that was because if I broke it up by the product rule for logs, it became ln of 5 plus ln of x. ln of 5 was a constant which went to 0. ln of x, variable function, which goes to 1 over x. It stands to reason that this is going to play out the same way. You can show the work, but it's not necessarily necessary, right? Because you can just kind of reason it out. But I'll do it anyway. ln of 4 plus ln of x, the derivative d dx of each of those pieces would go to 0 plus 1 over x, which would be 1 over x. All right. So that's that part. Okay. Then I'm going to bring the plus the ln of 4x. Then I just have to multiply by the derivative of 3x squared, which is just a 6x. So times 6x. And again, this is where x is greater than 0. These questions didn't ask us to simplify, so it's fine to leave it like this. But you know, there is some element of it where you're like, why wouldn't I just simplify that? That's fine. Either way, I'm just gonna move this because it looks like it's part of this solution. It really isn't. Just kind of throw it here. All right. So yeah, definitely a little bit more elaborate because it's got product rule, it's got log rules involved, but you know, if you take a systematic approach. Now, I want to be clear about this. I have a particular way of thinking about things. So my systematic approach, while it makes perfect sense to me, and I think it's a great way to do things, you might look at it and say, well, I don't like that method. It's not as convenient as some other approaches. That's fine. as long as you stay within the material learned within the course, like we were talking about last time with the student who had a tutor take their test for them, as long as the material that you submit is consistent with the material that we're learning in class, then I don't have a preference on how you write your answer, as long as it makes sense logically, right? I got to be able to interpret what you're writing, right? I got to know what you're going for. As long as you do that, you're good. All right. So let's flip over to page 32. This is where we talk about cases that don't involve a base E. All right, but we're going to use the techniques involving base E. So it's going to be a nice little review of what we've been working on. All right. So, and I also put here, you can see, I put a little table that has the little rules for you. So you can refer to that as you go. But I like to share the origin story behind some of these things because, I mean, you've gotten the impression, I've even said it directly, I'm not a big fan of saying, here's a rule, just use it. I like to get into why things work the way they do. All right, so I can tell you that there's a rule for figuring out the derivative of exponentials that don't have a base E, but I don't think that's beneficial without really talking about why it works the way it does. All right, so we have f of x is equal to 6 raised to the 3x minus 5. All right, if this were an E raised to the 3x minus 5, we'd be in good shape. It's not, so we are not yet in good shape. All right. So what I'm going to say is, it would be great, I'm not going to write that, but we would prefer this 6 to be an E. So want this to be E instead of 6. Guess it makes sense to have this with the arrow. All right. I want that to be an E instead of a 6. I don't like the fact that it's a 6. It's actually annoying me. All right. It's aggravating. It's like I gotta change the, for those of you who are into gaming and things like that, like I want to change the skin, I want to change the avatar, the look of it. So I want it to have a base E instead of a base 6. All right, so what I'm going to do is write an equation, E to some power, some unknown power, and you can use whatever variable you want for this. It doesn't make a difference. We kind of tend to use U for this sort of thing. So that's what I'll say is E to the U is equal to 6, solve for U. All right, so old pre-calc concept, actually even before that. All right, one way to solve for an exponential base E would be to convert it into log form, but I think an easier way would be to take the natural log of both sides. I think people are kind of a little bit more comfortable with that approach. So I just take the natural log of both sides, and then that allows me to apply the power rule for logs. All right, so just like we have power rule, product rule, and quotient rule for derivatives, we have power rule, product rule, and quotient rule for logs. All right? They just work completely differently and they mean something completely different, but they have a similar enough name to, of course, be confusing. All right. Oh, the 6 is still there. So the question was, where does the 6 go in the equation? It's still there. We're going to write an equation. We wrote the equation E to the U is equal to 6 to figure out a base and power combo that would allow us to replace the 6 with some other expression. All right. So we're going to write this as U ln E is equal to ln of 6. Right. And so ln of E is equal to 1. That's one of those log identities. And again, Desmos is very helpful if you're unsure of things like that. Yeah, I'm not sure. So ln of e, 1. All right. Same thing with trig identities. Cosine squared plus sine squared is equal to 1. Maybe you forget, type it in. All right. So u is equal to ln of e, which tells me, all right, because we started off, go back to what we started off with here, e to the u was equal to 6. That's what we defined. So now I know that u is ln of 6. So therefore, e to the ln of 6 is equal to 6. Now, you really don't have to show this work in order to come up with this relationship. It always just kind of boils down to this idea, but it ends up being like another rule. And, you know, some folks would rather do the work than memorize yet another rule. But what we can conclude is that e to the ln of a is equal to a. All right. Whatever constant you want could be represented as e to the ln of whatever that constant is. So let me just show you real quick. So let's say, well, I'll just use this one. E raised to the ln of 6 gives a result of 6. All right. So if I wanted to write the number 5 with a base e, I would say e to the ln of 5. 20, e to the ln of 20. Right. The only thing that it wouldn't work with would be negative numbers, right? Because you can't take log, or 0. You can't take the log of 0 or negative number. So this technique is only going to bear out when it comes to natural numbers. Well, really rational numbers, but on the positive end. All right. It's only positive rational numbers. You know what? Even irrational numbers. All right. So positive reals. All right. But since we're usually only focused on whole numbers, that's why my brain took me to natural numbers. Anyway, so I can now rewrite my original function at long last. Instead of 6 to the 3x minus 5, I can now write e to the ln of 6. All right, means the same thing. You're unsure? Type in your original function, x. They said 6 raised to the 3x minus 5. Parentheses. All right, so that's the original one that they gave us. This is what I'm putting in. I'll write it as y equals so that there's no confusion between the f of x's. So paren e raised to the ln of 6. Close it up, raise it to the 3x minus 5. And you see that we're looking at two graphs that are mapping to the same location. All right. And again, make one thicker and dashed so that you could really see the relationship. All right. So you look at this and say, well, okay, well, how is this going to help us find the derivative? Well, a power to a power, another property of exponentials, you multiply when you have power raised to a power. So this is the same as saying f of x is equal to e raised to the ln of 6 multiplied by 3x minus 5. You could distribute that. So it becomes e to the 3 ln of 6 times x minus 5 ln of 6. So all of this is what f of x would be equivalent to. And all of this was for the purpose of rewriting our function with a base e rather than a base 6. All right. So then we could apply our rule for base e derivatives. So d dx of e to the u is e to the u multiplied by du dx. So looking at this, I would then say, now using u multiple times in the same problem can be a little aggravating. So you just got to kind of look at this and say, we're done with all the stuff that came before. So now u is available to be used again as another variable. All right. So it's a different u now. All right. So we would let u be equal to the exponent, which would be, it's not pretty. But that's what the u would be equivalent to. And it's got ln's in it, but it's still a linear relationship. So when I find du dx, that x has a power of 1 multiplied by power by coefficient. You get 3 ln of 6, reduce the power by 1, x to the 0th goes away. This piece here is constant. There's no x in it. So that goes away also. All right. So my derivative f prime of x would be equal to e to the u. So all of this, all of that stuff multiplied by du dx. Now, whether you want to simplify it further and bring it kind of back to a base 6, that's up to you, but this would be equivalent, right? So, and like I said, there's shortcuts. We'll get to the shortcuts in a minute, but this actually shows you sort of the origin behind the shortcut, because anything that involves an e to the ln of 6 is actually going to be really something that can be replaced with a just a 6, all right? But really, if you think about it, all of this work here was to rewrite this expression. So it actually tells me that all of this stuff, no matter how ugly it is, this is really the same as saying 6 raised to the 3x minus 5. So our derivative is really 6 to the 3x minus 5 times 3 ln of 6, all right? Which actually leads us to the shortcut, right? It's kind of placed in a weird spot, but this is what the shortcut would be, which tells us, if you really look at it, we have some expression a to the u, not necessarily e. It's telling us to rewrite a to the u. So in this case, 6 to the 3x minus 5. We did that. That's this. Multiplied by the derivative. U prime is the same as du dx. Multiplied by the derivative of the exponent. So if I use my highlighter here, we did this piece. That's this. The 3 is the derivative of the exponent. And then multiplied by the natural log of whatever the base is, whatever the a value is. And you'd have it all in one shot. But, like I feel, and, I think there's got to be at least somebody out there that agrees with me, but I think it's worth doing it the long way at least once, so you get an idea of why things work the way they do. Otherwise, you're just memorizing rules. And some folks are just fine with that. They're like, give me the rules, I'll memorize them all day long. And then there are other folks that are like, I find no value in what we're learning if it's just memorization. Right? If I don't get a sense of the thought process behind it, I've learned nothing. That's really me. The exception to that would be like terminology. You got to learn the language of whatever subject area you're speaking or you're learning. Right? But it's actually pretty straightforward one way or the other, because, like, for example, I'll throw another example at you real quick. Call it a side example, but I'll take this as a typo. Let's say you have the derivative with respect to x of 2 raised to the x squared. All right. This rule is telling us that we have, we're telling ourselves that we have a base other than e, and that's an indication that we're using this rule. All right. So this is my a to the u. This whole thing is my a to the u. My quotes are a little out in the ether there. But the u would be equal to x squared. Du dx would therefore be equal to 2x. So I would say, all right, rewrite my a to the u, 2 to the x squared. U prime, that's the same as saying du dx, would be 2x. And then ln of whatever the a is. All right, the a would be the base. In this case, it's a base of 2, so I'd multiply by ln of 2. All right, so pretty easy if you're just using the rule, but without going through the build up to that rule itself. It's like, okay, I got a derivative. I don't know why any of that works. Right. Right. So that's exponentials. Now let's talk about logs. Logs, I think, are a little bit easier, right? Which is kind of weird because I mean, I don't know about you all on an individual level, but I do know that historically logs have struck fear into the very hearts of math students worldwide. No, I don't know if it's that bad, but it's I do find that when people are afraid of math, they're afraid of things like geometry, trigonometry, and logarithms. And everything else seems to be okay. Oh, I like math except for those crazy things, you know. So, but it might be a little weird for you to hear that this is actually going to be, I think, an easier process. All right, there's one rule that'll help you out a great deal, and that's the change of base rule for a logarithm. Right? Because just like with exponential e, we're given a log base 8, but I don't want a log base 8. I want a log base e. So I want to change the base here. All right. Now I'm just going to give you the relevant variation of this, because you could change a log base to whatever you want, but in most cases you want to change it to a log base 10 or a log base e. For the purposes of calculus, changing it to a log base e makes the most sense because we have some good rules when it comes to log base e. So let's say we have log base a of some argument b. Our change of base to get it into natural log form would be the natural log of b divided by the natural log of a. Or a little bit more usefully, 1 over ln of a times ln of b. All right, they both mean the same thing. It's just this variation right here is going to be the more useful one. All right. But if I wanted to, like I said, I could make it a log base 10. I could make it a log base 2 if I want. I don't. I want it to be a log base e. All right. So I'm going to take my f of x. All right. I'm going to identify the a and b value, quote unquote a and b values. The a value is the 8. The b value is the 3x minus 2. Okay. So I'm looking at 1 over ln of 8 multiplied by ln of 3x minus 2. All right, just by applying this rule here. A little over highlighting, but you get the idea, hopefully. So now I just got to find a derivative of it. All right, so the rule for natural log derivatives, d dx of ln of u is 1 over u times du dx. All right, that 1 over ln of 8, that's a constant multiple. Constant multiples just come along for the ride. So f prime of x would be 1 over ln of 8 multiplied by whatever the derivative of this is. All right, so off on the side here, what I would say is, all right, we're going to let u equal 3x minus 2. So du dx, well, x has a power of 1, so that's just going to be 3x to the 0th, so just 3. And the negative 2 is constant, so that goes away. All right, so this would become 1 over 3x minus 2, because that's what I called u, times du dx, which is just the 3. You could, I mean, if you want to clean it up a little bit more, you can. So we could say, or 3 over ln 8, you know, just kind of group our constant multipliers together, times 1 over 3x minus 2. All right. The one thing we're going to run into here is the domain restriction. Now, that might sound weird because we've been running into that a lot. And so it's like, what's so different about this one? It's not quite as simple as saying x has to be greater than 0, right? Because what we would need to do is take, in order to determine the domain, take the argument within the natural log function. Let's get a different color here. I'm going to go a little orange for those people who are at home. The expression contained within the natural log, that needs to result in a value that's bigger than 0. So for the domain, I would have to say 3x minus 2 is greater than 0 and solve. So add 2 to both sides. So 3x has to be greater than 2, meaning x has to be greater than 2/3. For quality 3, let me fix that. So my domain here is not as simple as saying x is going to be bigger than 0. I'd have to say x has to be bigger than specifically 2/3. All right, so where x is greater than 2/3. All right, so this would be my final answer. And again, just to make sure that we're all on the same page here, your final answer when it comes to finding the derivative of a natural log also must include a statement regarding any domain restrictions. All right, so if you omit that, then you don't get full credit. All right, so very, very important. You can't just ignore that. All right, so very, very, throwing a third four varies, 5 varies. Every time I say vary, I'm adding another vary, but it's so very important. All right. Now, when it comes to word problems, you know, any numerical cases, standing rule in the class, any situation in which you're asked to find the derivative at a point, you don't have to show me any work. I mean, if you want to show me the work, that's encouraged just for the partial credit aspect of it. But this could all be Desmos, you know, so like the application question, your percent of information retained T months after being tested on that information is given by this function model. Evaluate f of 2 and f prime of 2 and interpret your answer. So it's really the interpretation that we care about. But I can say f of t, since we're evaluating it, we could use the t, but you could also use x if you want, is equal to 82 minus 14 ln paren t plus 1. Close it up. All right, if you're interested in looking at the graph and you don't have, you know, you try zooming and you don't see it right away, then hit that little gear icon, take a look at the table, and you'll see that they're pretty substantially large. All right, so go back and then adjust this so that instead of going from like 0.169 to like 22, make it go from 0 to 100. Now, contextually, you should probably get there anyway, because it's saying the percent of information retained T months after being tested on that information is given by this. So you got to imagine that in this context, the maximum percentage would be 100. Like you retained all of the information, right? As opposed to, you know, like percent growth where you could have some value over 100. You could also make a case that, I mean, if you go above and beyond what's asked in a course, like if I expect you to learn 100% of the information in this course, but you take it upon yourself to study additional content related to the material that we're learning, you could learn 150% of the material in the course. I mean, that's I suppose possible, but it would be some number around 100. All right, so contextually, we should be able to get to the high value. All right, now after 2 months, this individual will have retained about 66.619% of information, right? So after, so f of 2 is equal to, well, approximate, I'm going to write the approximate form. And so that means that after 2 months, this individual has retained about, all right, I put the rounded form so I could say about 67% of the information. So that's fine. That's something that you could kind of conceptually wrap your brains around, I think. It's nothing too out there conceptually. You know, it's not like I'm asking you to draw a conclusion about something completely unfamiliar to you. You know, that's what I found I was doing whenever I would give sports related questions. You know, it's like you find out that 3/4 of the students had no interest in whatever sport I was talking about, but this is something that people can probably all relate to. Especially if you kind of forgot how to factor, you know, then you kind of look at it and say, oh yeah, definitely. There is a little degradation in the amount of knowledge that you have after you finish a course. You cram and study for the final exam, you pass it, you do a good job. And then 3 months later, it's like you never learned it. You know, that's a possibility. The, what you call it, I was gonna say the motivation, but it's really inspiration for this question had to do with summer vacation. You know, 2 months, students in high school and take final exams, Regents exams, AP exams. And then the next year, teachers all over are startled by the lack of knowledge that students come in with, as if they never learned the material at all. And if you ask the students, they'll say they never learned it. Oh, we didn't cover this last year, but they definitely did, but there's degradation of knowledge over time. So that was the inspiration of it. F prime, this is really why we're here. F prime of 2 is -4 2/3. I can make this a fraction just so it's easier to write. So F prime of 2 is -14/3, or you could say -4.6 repeated %, or you could round it to 3 significant either way. But the interpretation is what matters. All right. So after 2 months, this individual is losing about 4 to 5% of the information. If it were positive, I would say gain. Right? I'll say about 5% of the info. So if you put these two ideas together, what we're going to come away with is the idea that after 2 months, this person, when they took the final exam, they only had 82% of the information to begin with. How that was assessed, I don't know. All right. Some schools of thought believe that what you get on the final exam is the amount of information that you have retained for the course. But if you've ever taken a math final exam, and you all have in some capacity, you know that not every topic is equally represented. Not every topic is covered on the final exam. There just isn't enough time. So it's not a true representative of the amount of knowledge. And especially if it's it's a multiple choice test. Let's say you have, let's say it's 50 questions, 40 of them are multiple choice and the last 10 are free response. You're not getting any partial credit on the multiple choice, all or nothing. Even though it might have been a minor error, you get dinged for full credit. So it's not a true representative of the amount of knowledge that you have in a course. I would even argue to say your course grade is not a true representative of the amount of knowledge that you have in a course. There are some people who know math. They're really good. They know the material. They understand it. They just don't do well on tests. Right? Or I think this is probably a little bit worse. They do wonderfully on tests. They just don't do anything else. And they walk away with at best a C in the class, thinking, well, that C doesn't represent my actual knowledge. I got every question right on every test. I just didn't do anything else. You know, so that 82, we don't know where that's coming from. But let's say it's an accurate representative of the amount of knowledge a student has percent-wise for the content, let's say pre-calculus, at the end of the course. What this is saying is 2 months later, they will have the amount of information that they would have retained has dropped to 67% and is dropping at a rate of 5% per month. All right. So if you wanted to put the two ideas together, that rate of change is an amount of information that's being lost on a monthly basis. All right. Because if you really think about a rate of change, it's changing Y or changing X. All right. The X here is the percent of information. I'm sorry, the F of T is the percent of information. The T itself, which would take on the role of X, is the number of months. So we could say, for a more holistic sort of response, after 2 months, the students, assuming it's a student, knowledge or information has dropped to 67% and is dropping at a rate of about 5% per month. All right, so that's really just taking the two ideas and putting them together. All right, and if you're drawing a conclusion about a derivative, it's what I just boxed in blue that you'd probably want to look at. Like if somebody asked you, you know, to write a model that represents a situation, whether it's the amount of cars, you know, that are using a highway at any given time, you know, like when they put those little wires on the road, you know, like why are these wires here? You know, that's all that's doing is counting up the number of cars over a certain period of time. And so they make function models out of that, but they do it using computer systems. They're not actually doing the calculus. But yeah, they're just getting a sense of the usage of the road, right? That's a good question. Would it be 5% per month or 2.5 per month? Once you figure out the derivative at a particular moment, it's an instantaneous rate of change at an individual value of time. All right, so it's per unit of time. All right, so if I were to look at this as 10/2, for example, I could say that that's 10% per 2 months. But once it simplifies down to just the number 5, that's an implied 5/1. So that would be 5% per every 1 month. All right. So whenever you find the derivative at a point, it's always going to be a singular unit of change in the independent variable. So in this case, time. All right. 2 shouldn't be here. We're not talking about. Honestly, I accidentally copied this from my business calc class, so it's not relevant in this case. And I got a whole page for it. That's wonderful. That's a typo for somebody. You know, we'll do applications, but we don't want to get bogged down with it at the expense of the content. So implicit differentiation. I'm just going to take you through the problems on this page, and then I'll talk to you about the tech assignment, and then that'll be it. So with implicit differentiation, we kind of evolved to having the ability to take a derivative, not just for what we call explicitly defined functions, which are really just one variable solved in terms of another. All right, so you see in the explicit form in that table, y equals 1 over x. The y is alone on the left and the x is alone on the right. All right, but the implicit form, even though it's the same equation, if you were to solve that for y, you would get the explicit form. But in the current form, it's written as an implicitly defined function. All right, it's sort of like if you were to think about using a word in its own definition. You know, that's you're kind of along the lines of an implicitly defined function. It's just the idea here is if you have one variable that is defined in such a way that it is part of its own definition, then you're looking at an implicit form. All right, that's one application of it anyway. All right, but bottom line is, if you have x's and y's intermingling on either side of an equation, then you're looking at an implicit form. All right. So there's two ways to handle it. One would be to solve the equation for one variable in terms of the other, which is what we would have done up until and including last class and even the first half of this one. But now what we're going to learn how to do is find the derivative of implicit forms without solving for one equation in terms of the other. All right. So the process is there. It's a wonderful process, but it's very procedural, and it doesn't really get at why we do things the way we do them. So what I wanted to do is just kind of off on the side here, just take you through a very, very basic example of finding a derivative, and even going right back to the concept of a power rule. All right. So if we have, for example, y equals x squared, right? It's still an explicit function, not implicit, but I want to use implicit techniques to show you what this is all about. Okay. What we would be doing is taking the derivative of the left-hand side of the equation and also separately the right-hand side of the equation. Right? Now, this may sound weird, but when we write dy dx from y, there was actually a rationale behind why we were doing that. And it had more to do than just the notation of just saying, well, derivative means dy dx. Right? Or dy dx means derivative is really more appropriate. Right? What we're actually doing is looking at y as its own function. Right? Y is really, or can really be thought of as 1y to the first power. Right? Now, we have to, and this hasn't been relevant before, but we have to take into account that y can be equal to something. Now, we happen to know what it's equal to here. So that kind of cleans things up a little bit for us. But we also have to take into account that x can be equal to something else, all right, in terms of a function. All right. So that x squared can also be thought of as coefficient 1, just like the y is coefficient of 1. But x can be equal to something, maybe some function of t. All right. So we have to account for that. We got to keep that in mind. Now, the thing is, we've been thinking of x as always taking on a numerical value, but x can take on a variable quantity. I'll show you really quickly. They're called parametric equations. We don't do a whole heck of a lot with them just yet. It's more of a Calc 2, Calc 3 kind of thing. But if I were to take an equation, or I'm sorry, a point, like 1, 2. All right, it's very simple. What I'm saying here is that x is equal to 1 and y is equal to 2. All right, so the coordinate 1, 2 is really saying x is 1 at the same time that y is equal to 2. All right, that's all that a coordinate is telling us. Right, the intersection is actually the coordinate. Right, it's very, very straightforward. Right, but let's say I want x to be equal to some other function. Same thing with y. Maybe that function is some function of time. All right. what I could say is that, let's say, for example, x is equal to t plus 5. And y is equal to, because it really doesn't matter. I'll just say t squared. Just something that involves a t. If we know that every coordinate is x comma y, right? We had 1 comma 2. I can then say, all right, instead of the 1, 2, I could say t plus 5 and t squared. All right. The ordered pair would be based off of whatever I'm defining x to be and whatever I'm defining y to be. All right. So I could turn these off and just look at my curve here. Now it has a very short domain going from 0 to 1, but I can make it go from like negative 20 to 20. And so what we would have done is actually made a function that's based off of x and y being equal to other functions. So it's essentially a system of equations, right? So I'd have all this stuff here. These are the individual x and y's, put them together, and you can see that you're getting a brand new function that's related to the original, all right? So what does that have to do with this? Well, it has to do with the idea that we can no longer say that y is just going to be the number 2 and x is going to be the number 1. X and y could be equal to some other function, right? And it doesn't even have to involve the x, right? All we're doing is relating y and x to one another. All right. So when we take a derivative, we would take the derivative as if it were a chain rule problem. All right. And that's where things get a little interesting, because I would have to be thinking of y as being equal to some function u. All right. So I would let, and I'll just focus on the left-hand side here, let u equal y. Oops, almost wrote let u equal u. All right. If I were to take the derivative of both sides here, you know, well, I'd have to take the derivative of both sides, but if I take the derivative of u with respect to x, it becomes du dx is equal to, it's like, well, what would it be equal to? Well, I would have to take the derivative of this y equation, my unknown y equation, with respect to x. All right. And the only thing I can think of is to say, all right, I'll take the derivative of this y equation with respect to x. So you'd be right in thinking that I didn't really accomplish much of anything, right? Except, you know, incorporating even more notation. But that's telling me that du dx and dy dx would be the same thing. Right. So when I go to take the derivative here, whatever I'm calling my u, in this case, that's the y, is going to have a derivative of just dy dx. All right. So if I'm using the chain rule shortcut, I'd find the derivative on the outside. 1 times 1 is 1. Reduce the power by 1, 1 minus 1, 1 minus 1. And then multiply by the derivative of whatever I'm calling u, which I just got through saying is going to be dy dx. I mean, it's convoluted, it's confusing, but that's a true statement, right? The convoluted, confusing, and also the fact that it's dy dx, all right? The 1 y to the 1 minus 1, that goes away, because y to the 1 minus 1 is y to the 0th, and anything to the 0th is equal to 1. So the whole left-hand side equals dy dx. All right, so that's a lot of explanation for something that we were just taking on faith. All this time I was saying y becomes just dy dx. Why? Because I said so. Because dy dx means derivative, right? But there's really an analytic justification for it based off the fact that y could be some other function, right? The same idea would hold true on the other side, right? So we would do all this stuff again, just with the x, right? So since we're done with the u here, I could use the u all over again. But I could also use a different variable if I want. It really doesn't matter. But you could kind of look at it as two separate instances of u. I would let u equal x, right? Whatever the base of the expression is. So du dx would be equal to, well, x could be some other function, and I don't know what that function is. So all I could say at this point is that I would just take the derivative of this x function with respect to x. But then you look at it and say, okay, yeah, all this theory is well and good, but dx, notation-wise, dx divided by dx is equal to 1. All right, that's inescapable. Like we can't avoid that. So this does become a 1, with the idea that if we're taking the derivative of a variable, even though it might represent another function, with respect to the variable itself, it's always going to go to a 1. All right. But then I would take the derivative of the 1x squared. 2 times 1 is 2, x to the 2 minus 1. But then I would multiply using the chain rule shortcut by du dx, which we just established was equal to 1. And so this whole thing would simplify down to just a 2x. So the left side simplifies down to a dy dx. The right-hand side simplifies down to just a 2x. Right? So then we can conclude that dy dx is equal to 2x. Now you look at this and you say that this is New York to New Jersey via Montreal. You know, like this is definitely a roundabout approach for saying that the derivative of y equals x squared is dy dx equals 2x. But this is actually going to set us up for this concept of implicit differentiation, because what's happening, or what we get from this, is the idea that y doesn't just become a dy dx through derivative taking, right? The derivative process, right? Process is the word of the day, by the way. So once again, process is the word of the day. What happens is there is a procedure or a process that allows us to determine that y becomes dy dx through the process of differentiation. I know I'm using process an awful lot now, but it is the word of the day, so why not? And that's what's going to lead us to understanding the concept of implicit differentiation. So let me just show you example 1. All that theory is all well and good. I remember being exposed to the theory as a student and having the thought of like, that was interesting, and I'm sure one day in my life I'll understand it, but that day is not today. Let's see how you actually solve some problems, and then maybe I'll circle back to understanding the theory part of it. So that's understandable. But I'm given x squared plus y squared is equal to 16. I can graph that. This is one of the benefits, one of the many benefits of Desmos, is that it's not just restricted to functions. It'll graph any kind of relation. So we know what we're up against here. I want to find the derivative implicitly. So what we do is take the derivative of each term separately, and then just put it all together after the fact. That x squared can be thought of as 1x squared. The y squared can be thought of as 1y squared. Right? Each one of these variables can themselves be other functions. So we allow for that by applying the chain rule. So I would say power multiplied by coefficient, so 2, x to the 2 minus 1, but then I multiply by the derivative of that inner function, x, which would be d of the x dx. Right, so whatever's contained within the function chain rule gets multiplied on at the end. In this case, that expression is a very simple x. And the benefit here is, like we were talking about before, this cancels to just a 1. So the short version is you didn't really have to do that. For x's, you don't really have to multiply because it's always going to cancel out. But for the y, 2 times 1 is 2. Y to the 2 minus 1. Understanding that y could itself be another function, we multiply by the derivative of that y with respect to x. The right-hand side is constant, so that goes to 0. So it's like, all right, well, at least there's something understandable at all of this. But when you simplify, we get 2x plus 2y times dy dx is equal to 0. Then our last part of the process is to just solve for dy dx. All right. So I would subtract the 2x from both sides. So I'd have 2y dy dx is equal to negative 2x. And then I would divide both sides by 2y. And I'd get, if we simplify, dy dx is equal to negative x over y. All right, so that's the derivative using implicit differentiation. Now it's just a matter, well, it says find all points where the graph has a horizontal tangent. Horizontal tangents those occur when the derivative is equal to 0. Because horizontal lines have 0 slope. So all I would do is take my derivative, which is negative x over y, set it equal to 0 and solve. Cross multiply, get negative x equals 0, meaning x is equal to 0. So I'd be thinking about whenever x is equal to 0 on this graph. So I could type in x equals 0. That's the y-axis, make it a little bit more vibrant. All right, so where that graph intersects the circle would be at 0, 4, and 0, negative 4. All right. So that would be, those would be instances in which the graph has horizontal tangents, because if I draw tangent lines at those locations, they would necessarily, in order to touch in only one location, they would necessarily have to be horizontal lines. Right. So when it comes to the vertical tangents, and honestly, I don't know where this instructions are coming from. This is ridiculous. And this actually should be on the previous page, but it's there, so we'll work with it as is. So where the graph has a vertical tangent, dy dx would be undefined. Undefined as in 1 over 0. It could be anything over 0, but it would always simplify down to 1 over 0. All right, so since I know dy dx is negative x over y, I could cross multiply and I'll get y equal to 0. So then I would look at my graph and see where y is equal to 0. That happens here and here. And so now we know that at 4, 0 and negative 4, 0, we have vertical tangents. There's the only way that you could draw a line there, that would be vertical. I'm sorry, that would be tangent to the curve, would be is if it were a vertical line passing through those points. I'll just put this here. Looks a little nicer. Okay. So, you know, it's a little heavy in terms of the conceptual reasoning and all that stuff, but what people kind of take away from this is, all right, I'll just rely on the procedure until I understand the concept. And then eventually the understanding of the concept comes, and then everything just kind of works itself out. So the little ingredients that you want to take away from here is, first, for x terms, take the derivative the way you normally would. So take the derivative as usual. For y terms, take the derivative as you would an x term. But then multiply by dy dx. All right. So let me just show you that in action, because I know it could be a little jarring, this implicit differentiation. And I can tell you that when I first learned implicit differentiation, I actually had to go and stay after school for extra help. It was like one of 3 instances where I ever stayed after school for math. The other 2 were disciplinary. I had to stay after because I was cutting class. So bad example. That doesn't really help anyone, I guess, except to show that I'm human. But the one time that I did of my own accord was because I didn't understand implicit differentiation. So if you don't get it the first time, maybe you'll be a math professor before it's all over. Okay, so x squared y plus y squared x is equal to -2. If I'm going to take the derivative of this using implicit differentiation, first thing you would probably recognize is that if you can solve this for y, it's not going to be easy, right? There is a way to do it, but it involves completing the square, and it's not pretty, right? But I'm looking at the product of 2 factors here and the product of 2 factors here. So I got to do the product rule twice. We'll focus on them one at a time. So for the x terms, take the derivative as usual. Okay, so keep that in mind. So I have my first function, x squared, times the derivative of the second. So for y terms, take the derivative as you would an x term, but then multiply by dy dx. So I'm looking at this y and I'm pretending it's an x. All right. So I have a 1 as a coefficient, 1 as an exponent. So I'd say, well, what would it be if it were 1x to the first? I would have 1 times 1, which is 1. It would be x to the 0th power, but it's really not an x. It's a y, so I'll use a y there. But because I took the derivative involving a y term, I will then have to multiply by dy dx. All right, so that's the derivative of my second term, plus the second term, just plain old y, times the derivative of the first term, x squared. Take the derivative of that as I normally would. That's going to just be a 2x. Nothing fancy there. All right. So moving on to the second piece, I have 2 parts to that. Get a green, oops. Come on, undo. Get a green involved here. My first would be y squared times the derivative of the second term. Well, x, that's an ordinary x, so derivative of x is 1. Plus my second term, x, times the derivative of the first term. All right, that first term, y squared, I'm going to pretend in my mind that that's an x squared. All right, so derivative of x squared would be 2x. All right, so 2y. But because I took the derivative of a y term, I now have to also multiply by dy dx. All right, so It's conceptual versus procedural. This is procedural. Right-hand side is constant. Constant goes to 0. So this is a derivative. It's a derivative equation, also known as a differential equation. But we can clean it up further by just really getting rid of anything that doesn't need to be there, like the y to the 0th power. So x squared dy dx plus 2xy plus y squared plus 2xy dy dx is equal to 0. Now what we need to do is solve this for dy dx. So what I'm going to do is hang on to any expression that has a dy dx attached to it. Everything else we got to move out of there. So I'm going to subtract a 2xy. I'm going to subtract a y squared. So I would have x squared dy dx, I'll get to the chat in a second, plus 2xy dy dx is equal to all that stuff on the right. And then I have to factor out a dy dx on the other side. Why is the y on the left side 1y to the 0th power, but on the right side it's just 1, not 1x? Well, 1x to the 0th power would be 1 anyway. So that's what I was saying. When we take the derivative of an x term, we take the derivative of it the way we always would, right? So you look at the x and you say, okay, derivative of x is 1. Why? Because we've done that 100 times, right? So, but the y stuff is unfamiliar, so I'm showing the extra step there. But that's a 1, right? The right-hand side should actually go to 0 because we're taking the derivative. The derivative of -2 with respect to x, right? And the derivative of a constant is always going to be equal to 0. Right? So I'm going to factor out a dy dx. It's going to leave me with x squared plus 2xy. Right-hand side, -2xy minus y squared. And then it's just a matter of dividing. Not pretty, but this is what our derivative is going to be. Okay, so this would cancel. And this expression here would be, I mean, like I said, not pretty, but this is dy dx. All right. So the second part to this problem actually is something I've been meaning to change for like a solid 15 years. It really kind of doesn't make a whole heck of a lot of sense in this situation because this isn't a function. So to use function notation, I don't even know what I was thinking. So that shouldn't be there. And this should just be a one-part problem. And so what I'll do is put a star on example 3, have a look at that, 3 and 4. They're actually simpler problems than what we just did. But implicit differentiation, oh yeah, this is glorious. Look at this. I don't even know. Yeah, there is no example 5. But that's a typo for somebody, so collect those typo bonus points. All right. But yeah, I kind of ran a little long with the lesson, so I'll do the tech assignment overview next class. I don't want to hold people up if they have questions and so on. So, but that's where we'll leave it for tonight. We'll continue talking about implicit differentiation next class, and then we'll get into some word problems associated with implicit differentiation. There's actually, if you're open-minded about it, this is where calculus starts becoming more interesting in terms of like why we're learning what we're learning. So so yeah, be on the lookout for these applications being a little bit more relevant to stuff that you might be familiar with in your everyday life, right? So, but I'll stop scrolling around here because that's distracting. All right, so let me stop the recording.